So far with rotation, we've kind of taken some analogs from like force and work. So like work was force times displacement, and so like the rotational analog for that was that work was equal to the integral of the torque with respect to the angular displacement. And so we kind of compared force and distance. Well, if you remember, we also had a chapter where we talked about force as the rate of change of momentum, okay? Because F was equal to delta mv, okay, which is basically the rate of change of momentum. So force causes change in momentum with respect to time. Well, we've done the rotational analog for relating force and displacement. Now it's time to talk about the rotational analog for comparing force and time. So just like we have linear momentum, we also can have angular momentum, okay? And just like to find torque, we multiplied the force times the radius. To find angular momentum, which we'll call L, or which we'll use L to symbolize, we multiply the momentum times the radius, okay? And the actual correct way to do it is that the definition of angular momentum, and they like to use the lowercase l for angular momentum of a particle. So the angular momentum, cursive lowercase l here, is equal to r cross p. Okay, so just like with torque, they have to be perpendicular. Okay, and this is kind of a different way of kind of thinking about the world. Okay, because you can find the angular momentum of any object or on any point, and it's just, I mean, it's all you have to do is times momentum multiplied by the radius. Okay, and the cross product is a clue to you that if you can find the perpendicular radius and multiply by the momentum, that will give you the angular momentum as well. Okay? Now, before we get started, this, in my mind, is one of the most powerful concepts we'll discuss in this class, and it's a little bit difficult to conceptualize just like because we're limited to our experiences in this world governed by things being fixed to the ground from friction, but this is really kind of the thing that runs the universe, I guess you could say. And we'll talk more about conservation of angular momentum later, which is just a really, really, really important concept. Okay, so because angular momentum is equal to r cross p, one of the ways that we can find it, that's r cross mv. Since mass is a scalar, we can kind of pull it out to the front. So it's equal to m times r cross v. Okay, so this would be our definition, or just another form of angular momentum. So if you know the velocity of something, its radius, you can multiply the perpendicular versions of them, or use the cross product to find the perpendicular product of them, and then multiply by the mass. Okay, and then as I was saying, as the force is the rate of change with respect to time of momentum, torque is the rate of change with respect to time of angular momentum. Okay, because if you just tack on a radius here, you get torque and angular momentum. Okay, so so like just like the product of force and time gives you change in momentum, the product of torque and time would give you change in angular momentum. Okay, so let's go ahead and give this a try. See if we can find the angular. Actually, let's do a couple samples real quick. So let's say we are in a car. Okay. With really big wheels sticking out to the side, and we're going this way. Let's say the car has a mass of 500 kilograms, and let's say that it's traveling 20 meters per second. Let's say that there is a stop sign right here that's about 5 meters from the road. Okay, or maybe it's like on the other side. So the car's going to pass within 5 meters of it. And the question is, what is the angular momentum of this car about the stop sign? Okay, well, to do this, we want to find R cross P or M times R cross P. So we could say that this is the radius, and that's the velocity, and then we'd have to find the perpendicular versions, or we could like write vectors for them and do all that. Or we could look to see where it's going to pass closest to the stop sign. Okay, because the place where it passes closest is the place where we have a perpendicular radius. Okay, so as this car drives along, the place that it passes closest is this distance of 5 meters. Okay, so instead of using the cross product or having to use sine to find the perpendicular radius, we can just see the point where it passes closest to it. Okay, and so its velocity, or it has a mass of 500 kilograms. Okay, it has a velocity of, let's say it'll pass by within the closest distance of 5 meters, and then it has a velocity of 20 meters per second. Okay, which gives us an angular momentum of, let's say, 5, 0, 0, 0, 0. Okay, so that's like 50,000 kilogram meters squared per second. Okay, and then the fact is that we can actually find angular momentum like this around any point. Okay, but what's going to matter is later when we compare these and when we find changes in it. Okay, let me give you one to practice. Let's see. Let's say that we have an object. Okay, or let's say that we have a someone playing baseball. Okay, and so this would be the person. So this would be the pitcher, maybe. So we can throw the baseball, and then here's the batter. And that playing baseball. Okay, and the ball's going to fly past him. Okay, as it flies past him, this pitch is going to be traveling, say, 20 meters per second. Let's say the ball has a mass of about 0.3 kilograms, and it's going to come within, if we have like an overhead view here, here's the batter. Okay, the ball is going to come within, let's say, a distance of 40 centimeters or 0.4 meters. Okay, and so what I want you to do is find the angular momentum of the ball about the batter. Okay, which means in respect to this batter. Okay, and so go ahead and do that calculation. Okay, so you're going to multiply m times r times v. Okay, and this is the perpendicular radius. So the place that the ball will be closest to the batter is 0.4 meters when it's passing him. So it would be 0.3 kilograms times 0.4 meters times 20 meters per second. Okay, which will give us an angular momentum of, I believe this should be 2.4 kilogram meters squared per second. Okay, and that would be our angular momentum for this baseball about that batter. Okay, so let's look at a couple more samples here. The next one to look at is this. Okay, so we have a series of particles. Okay, there's these two. Oh, let's go back to the baseball question actually. Okay, and to the and then we mentioned the one before. Okay, so one thing we didn't talk about is which direction this is. if this baseball, at the point that it passes him, was rotating about this batter, or if you were to somehow catch it with a string and bind it to him at this radius, it would start to rotate about him this way, which means that in this case, this is a positive angular momentum. Similarly, with the example with the car, if somehow it got like tied to the stop sign at that point, it would have rotation this direction, which would be positive. Okay? So what that means for us is this. Okay, we have this sample problem here, this checkpoint from the reading, and it asks to rank these 5 particles. They all have the same mass based on their angular momentum. Now, you have 3 that are traveling in a straight line and 2 that are rotating. One of the things I hope you realize so far is that to calculate angular momentum, the magnitude of it has nothing to do with whether or not an object is bound to the object it's rotating. Okay? So, essentially, 2 objects, or any object traveling past something else, can have angular momentum about that object, whether it's rotating right or not. So it's asking, rank the particles according to the magnitudes of their angular momentum about point O greatest first. Okay? So, the angular momentum is equal to m times r cross v. Okay? So if they all have the same velocity and the same mass, then their angular momentums will depend on the radius. So objects with the greatest radius will have the greatest angular momentum. So object 1 here is the distance 2r away from O. Okay? So that one would have the greatest angular momentum. Does anything else have the same angular momentum as object 1? Well, if we look over here, we see object 3 is going to have that same distance as object 1 as it passes by O, which means that 1 and 3 are actually tied. Okay? From there, we're going to say, okay, well, 2 and 4 are that next distance down. Okay? 2 is at this distance r away, and then 4 had passed by it at that distance r. So even though it's already gone past it, if we trace its motion back, the place that it passed closest to it is the same as the distance for 2 there. And so 2 and 4 have the same amount. And then finally, object 5, if you trace it back, it's traveling straight through the point, which means that it has 0 angular momentum, so it has the least. Okay? And the next question is asking which ones have negative angular momentum. Well, negative would be clockwise. Okay? So object 2 is rotating clockwise. Okay? 1 is rotating counterclockwise, so that's positive. And then let's look here. Okay, so think about what I was saying before. If you were to bind an object to this point and force it to rotate, which way would it go? So this one would be forced to rotate that way, which is counterclockwise, which is positive. Object 3 here would be forced to rotate this way, which is clockwise, which is negative. So 2 and 3 have negative angular momentum.